Here's another spectrum. I think I got this one off the internet somewhere, which, by the way, you can look up lots of examples of NMR spectra just by Googling NMR in the internet, and some of them are kind of complicated, but many of them come from courses just like this, and the more of them that you see along with their structures, the more you get to a point that you can look at a spectrum and start to immediately associate certain peaks with certain features. And again, that's something that's part of the worksheets and part of the homework problems, where you're given information about a spectrum, or the graph is given to you along with some clues about what the molecule might be, and your job is to assign the peaks to the different hydrogens in the molecule, and if need be, figure out how it's put together. This spectrum is not labeled as such, but this big peak here, big tall one, is 3 times as big as the other peak. And so that means that since they're in a 3-to-1 ratio, the bigger one is associated with 3 times as many hydrogens. Now, for this molecule, that means what we have is actually a set of 9 hydrogens, these 3 methyl groups, as opposed to the set of 3 hydrogens with the methyl group on the left. So that's a 9-to-3 or 3-to-1 ratio. And when you have 9 equivalent hydrogens, about the only way that's going to occur is if you do have 3 methyl groups that are all attached to a single carbon. So in other words, this is kind of a tertiary butyl group, which generally will give rise to a very tall peak there in the spectrum compared to the other peaks. And this other methyl group, again, we've seen this a couple times. When you have a methyl group that's next to a carbonyl, the resonance is a little bit over 2. That's a 2.0 down here. You can hardly read that. Whereas methyl groups that are attached to carbons where they're further away from oxygens, which is the case like this, here this is 1.5 right here, so you've got a resonance here of a little bit less than 1.0. And methyl groups, when they are not near oxygens or chlorines or bromines or halogens, typically their resonance is among the lowest. Here's another phenomenon that really makes NMR a useful tool. Again, we get different peaks for different sets of hydrogens. The size of the peak is proportional to how many hydrogens are giving rise to the signal. That's great. Here's another feature that can really help you piece together pieces of a molecule, letting you know which carbons and their hydrogens, how they're connected to their neighbors. And that has to do with this thing here, the splitting of signals. So in this molecule, this is a 4-carbon ketone, that is butanone, and butanone has 3 sets of hydrogens. The 2 methyl groups here are not equivalent. One is directly attached to a carbonyl, the other is not. And certainly a carbon with 2 hydrogens is not going to be equivalent to one that has 3. So we expect 3 signals, but there's a little bit more going on here. You can see the way these are labeled. The 3 H's is one of those methyl groups, but there's another 3H signal that's not as tall because it's being split. And again, it's the area underneath these curves that is associated with how many hydrogens they're responsible for. So just because we have 3 hydrogens that are equivalent doesn't mean we get a tall single peak. Sometimes it is split into other peaks. And what's going on here is that the 3 hydrogens here that are outlined in pink, they are giving rise to this signal at the far right. And what is shown is that if we expand that signal, and that's what it looks like over here, so this is oftentimes done if we need to see some detail of what's going on with this peak, it is expanded over here. And what we call this thing is a triplet. It's 3 peaks, 1 big one, 2 smaller ones, but you can see it's got a lot of symmetry to it. And that splitting is due to the influence of these CH2 hydrogens that are right next door. And at the same time, these 2 CH2 hydrogens, again, they give rise to this signal here around 2.5 or so. But when they expand this, what you see is a set of 4 peaks. So those 2 hydrogens are actually split into 4 peaks. That's called a quartet. And they're split because of the influence of the neighboring CH3 peaks. The other peak here is just a singlet, as it's called. It is not split at all. It's just a tall, thin spike. and that's due to the methyl group that is way over here on the left. And what that methyl group has that's different is that it's not immediately adjacent to a carbon that has its own hydrogens. So this rule at the bottom, a very important one to be able to apply because it shows up a lot. The N+1 rule. And as it says there, any signal, any set of hydrogens, their signal will be split into a number of peaks. And as it says, it's split into N+1, where N is the number of hydrogens on an adjacent carbon. So it's easier to kind of see some examples of this to make sense out of that sentence. But again, these two hydrogens here, they're split by the methyl hydrogens next on the carbon next to it. And the reason why they're split into a group of 4 signals is because they're being split by 3 hydrogens. So that 3 + 1 gives us 4. At the same time, the methyl hydrogens are split into 3 peaks. So N+1 is 3. That means that's happening because they're being split by 2 hydrogens that are neighboring. So again, the size of the signals is proportional to the number of hydrogens giving rise to them, but the splitting tells you about what's going on at an adjacent carbon. And as it says, you have to have carbons that are close to each other, and they have to have non-equivalent sets of hydrogens in order for them to split each other's signals. But when they do that, that tells you something about the connectivity of molecules. And the more hydrogens you have, the more carbons you have, the more information you are going to want to really be able to say exactly what structure goes with a particular spectrum. That rule of splitting is part of this pattern here. This table shows that when we have a splitting caused by 1 hydrogen, N+1 is 2, so we get a doublet, 2 peaks that are going to be the same size. And so the intensities 1 to 1 tells us that a doublet does have 2 equal size peaks. What we just saw are examples of, well, an example of a triplet and a quartet in that previous spectrum, if you flip back to that one. And for a triplet, the peak in the middle is about twice as big as the ones on either end. It's not always exactly 1 to 2 to 1, but it's pretty darn close. Quartet has 4 signals, but the 2 in the middle tend to be 3 times as big as the ones on the edge. And we'll see examples of some of these other splitting patterns as we go along. And so would we need to have information about that splitting? An NMR spectrum will give us that. This thing over here, by the way, is called Pascal's triangle. You sometimes encounter it in math class, and it's a pattern that, again, shows up in the interpretation of NMR spectra. So this is a good table to have handy as we go along.